Overloading in radial distribution network. Under that we will study overload due to active power flow only. Consider a location along a distribution feeder where it has been operated radially. So here the downstream of consumption, which is represented by P CONS of T, that is consumption, P consumption of T, and the downstream generation is represented by P generation of T. Two parameters are defined here. One is downstream consumption, which is represented by P consumption of T, and the downstream generation, which is represented by P generation of T. The active reactive power flow are neglected, so that the total power flow in this location is given by, the total power is represented by the P of T. P of T is equals to P consumption minus generation. P consumption of T minus generation of T. So here we assume that no overloading situation that is existing before an introduction of this distribution generation. There is no overloading. So as long as the maximum power flow after consumption is less than that of before, so there will be no overload. So in this condition, the power maximum, it is stated by the power maximum will be less than power consumption maximum, where the power is consuming is maximum will be less than the power maximum that is available with us. It will be maximum. With large amount of generation, the maximum power flow occurs through the maximum generation and the maximum consumption as well. So here the P max can be defined as the power that is generated maximum to the power that is consumed, which is minimum. The power maximum is defined as the power generated at a maximum level to the difference of the power consumed at a minimum level. So in the figure, what you are seeing is an example of feeder. So we can guarantee that there is no overload. So it consists of four approximate successive points that is defined as A, B, C, D. At B there is one load, at C one feeder, and D is one feeder. Okay. Here the power generation maximum is usually less than the power consumption minimum plus the power consumption maximum. This criteria should be fulfilled for every location on the feeder. So this sufficient requirement that could be used as a first hosting capacity level. As long as the maximum generation is less than the sum of minimum and maximum consumption, there is no chance of occurring of overload. So whenever the maximum generation exceeds the first hosting capacity for the location along with the feeder, the additional studies are needed to determine the secondary hosting capacity. The second hosting capacity is reached when the maximum current become equal to the ampacity of this feeder section. So this should be less than the maximum permissible power. So which is given in our third equation. What we have seen that power maximum is equals to power generation maximum minus power consumption minimum. Here the difference of the power generation maximum to the power consumption minimum will be less than the maximum power that is available to us. That is power generation maximum, the difference of power generation maximum and the power consumption minimum is usually less than the power maximum limit. So which results in the following condition. power generation maximum is usually less than the power maximum limit plus the power consumption minimum. These are the following equation that we have studied from our active power flow. Moving on, let us see that active and reactive power flow. When including the contribution of this reactive power to the current, the expression becomes even more complicated. We know that the methodology will remain same. The maximum apparent power for a feeder section without generation would be equal to. So here the maximum apparent power for a feeder section without any generation is given by S max, 1 is equals to root of P consumption at a maximum square plus the Q consumption maximum square. So where P consumption maximum and Q consumption maximum are the maximum active and reactive power consumptions. So here the P consumption maximum square represents the active power and the Q consumption square represents the reactive power consumptions respectively. Here it is assumed that the variation in active and reactive power are same, so that the maximum reactive power, here it is assumed that the time variations are in active and reactive power demands are same. The time variation in active and reactive power, it is same. So maximum reactive power is reached when both active power and reactive power consumptions are at their maximum. Point to be noted, the maximum reactive power is reached whenever this both active and reactive power consumptions are at their maximum limits. When active and reactive power consumptions show significantly different in variation with time. So this should be included in our study. So in this case, the time domain simulation, it might be an appropriate solution for that. Some examples are given here with a sustainable amount of generation that is connected to feeder. The maximum apparent power is reached for a minimum consumption and also for a maximum generation. So consider an example here. So which shows sustainable amount of generation which is connected to the feeder. The maximum apparent power reached for minimum consumption and the maximum generation. Here the maximum amount of apparent power which is reached for minimum consumption and the maximum generation is depicted by the following equation. That is S max, 1 is equals to root of power generation at a maximum minus the power consumption at a minimum to the whole square plus Q. P refers to active power, Q refers to reactive power. Q square consumption minimum. This can be also stated as the root of the active power generation at a maximum level minus the active power consumption at a minimum level to the whole square plus the reactive power consumption at a minimum level. Where it is assumed that the generation here neither produces nor consumes the reactive power. The maximum apparent power with the generation should be always less than this maximum apparent power without any generation. the maximum apparent power here with the generation is stating that with the generation should be always less than this maximum apparent power without generation. So this is represented by another equation, that is S maximum 2 will be always minimum when compared to S maximum 1. Here S maximum 1 represent the maximum apparent power with the generation, and S maximum 2 is the maximum apparent power that is without generation. So from this equation we can state that the maximum apparent power with the generation should be always the less than maximum apparent power without generation. So this results in the following expression, that is for a first hosting capacity, active power generation at a maximum level should be less than active power consumption minimum plus root of active power consumption square for a maximum plus reactive power consumption at a maximum minus the reactive power consumption at a minimum. Also further you can write this as a so the bracket you can reproduce this what is it, equation in a bracket form, that is you can also write this as a root of active consumption at a maximum level plus a bracket of the reactive power consumed at a maximum level minus reactive power consumed at minimum level to the whole square. No problem. You can also duplicate the equations like that. The second hosting capacity is reached when the current through the feeder section reaches the ampacity of the feeder. The maximum current or apparent power, this should be less than the maximum permissible apparent power. So which results in the following expression. Here whenever the secondary hosting capacity is reached, whenever this current feeder section reaches the ampacity of the feeder. So again this should be less than the maximum permissible apparent power. So here Pmax gen will be less than that, active power will be less than the active power consumption at a minimum level plus a root of S square maximum limit, that is apparent power that is consumed at a maximum level minus the reactive power that is consumed at a minimum level. So this is our final expression for the both active and reactive power flow. So in this session we enclosed one derivation based on overloading on distribution network, that is active power flow that is caused due to only active power flow, and both considering active and reactive power flow with an example of feeder.